Okay, so welcome everybody to this first event of the 2025 winter edition of the AI Spotlight seminars, which is organized by the Italian Association for Artificial Intelligence and the AISB, Society for Study of Artificial Intelligence and Simulation Behavior. Today we have a talk that will be provided by Anthony Cohn by the University of Leeds. And before leaving the floor to Bertie Mueller for introducing our speaker, I just want to tell you that we have two other scheduled talks for this winter series, which are the talk by Bernardo Magnini that is scheduled for February 27, and the one by Alessio Lomuscio that is scheduled for March 21. So please take notes, and we hope to see you also for the next events. I will leave the floor to Bertie for introducing our today's speaker.
Thanks, Antonio. And I'm very happy to introduce Tony Cohn as our speaker today on behalf of AISB. Tony used to be chair of AISB and indeed is now fellow of AISB. And amongst many other awards, can I highlight that he won just last year 2 distinguished service awards, one from ECAI and one from the Principles of Knowledge and Representation and Reasoning, KR conference. So very well established with many years, many decades indeed, of AI research in knowledge representation, in qualitative spatial reasoning, robotics, cognitive vision, and ontologies. And we're really excited to hear your talk tonight on common sense reasoning and large language models. So thanks for joining us, and thank you, Tony, for making time to give this talk. Over to you.
Okay, thank you very much indeed for inviting me. A great honor. I'm very happy to give this joint talk to AISB and IA. So this is my title of the talk. Of course, I'm not going to be able to talk about all of common sense reasoning. I'm just going to give you a little bit of introduction, to, particularly focusing on the work that I've been doing over the last couple of years or so. So, of course, as we all know, LLMs are a very active research area. We've seen a huge amount of stuff in the press just this last week with the release of DeepSeek and the response to it from OpenAI and many others. And many claims are made about the ability of these language models to do reasoning. And so the question I'm going to be addressing here, to what extent they can do common sense reasoning. I'm mostly focusing on unimodal models. But if I have time at the end, I'll talk a little bit about multimodal. This is all part of the work I've been doing at the Alan Turing Institute, which is the National Institute for AI and Data Science in the UK. It's a joint project with Nigel Shadbolt and Michael Wooldridge, where we're looking at particular 3 areas of reasoning: a theory of mind, alignment to human values, and the area I'm focusing on, common sense. So I'm going to be particularly, in fact, focusing on spatial reasoning, because that's something that's been dear to my heart since, I guess, about the mid-80s. But not, I will say, not all the spatial reasoning I'll talk about today is necessarily common sense reasoning. So, I mean, we might ask what kind of spatial reasoning to test. And again, it's something I've been working on for many years now, is qualitative spatial reasoning. And that kind of fits in very well with this whole theme of common sense reasoning, because the way we use, talk about space in everyday parlance is we talk about, you know, the water in the cup, the computer on the table, you go through the door. We tend not to use metric information. We tend to talk about the world in this very qualitative way. And so particularly we're using very topological relations, things like in and touching and so forth, directions. We might be talking about shapes, distances, trajectories, route descriptions. We might be bringing in time as well. There might be specific geographical spatial reasoning, if, for example, involving cardinal directions. So what exactly do we mean by common sense reasoning? I'm going to point you all to this very nice paper by Ernie Davis, which originally came out on Archive at the beginning of 23, but then was published in ACM Computer Surveys, where he looked at benchmarks for automated common sense reasoning. And it's a long paper, so you don't have time to cover all of that, but let me just take a few highlights from it. He says it's integrated with other cognitive capabilities, language, vision. One almost never observes it directly, only how it's manifested through action, through language, and so forth. But it's independent of any particular modality task. It's the kind of information, the knowledge that we might use and reuse in multiple situations. It has broad scope, it's not domain specific, it's covering things like time and space, common sense, physical knowledge, biological, social realities, meta-knowledge, and so forth. And it's distinguished from common knowledge, which is everyday facts about the world, such as that Keir Starmer is the current Prime Minister of the UK. That's not common sense reasoning. It's just a fact which happens to be true, which many people might know, but it's not what I'm interested in here. And we're so interested in generalities rather than individuals. It's not the kind of thing gets taught in schools or you learn from books, as many specialist domains are. And Ernie Davis gives lots of desiderata for common sense reasoning benchmarks, and notes that many benchmarks which purport to be testing common sense reasoning actually don't. And so he's got this list of benchmarks on his website, which you can take a look at. And there's many problems amongst those, and these are some of the issues he highlights. You often get leakage from the benchmark into the training set of the large language model. Of course, this is not unique to common sense reasoning. It's a general problem for large language models. You may have lax evaluation criteria. So, for example, the very well-known so-called Winograd Schema Challenge, which was popularized by Ernie Davis and also Leo Morgenstern and Hector Levesque. And you have one example of such a Winograd Schema Challenge instance here. The trophy wouldn't fit in the case because it was too big, because it was too small. And I've chosen this one because it's a spatial reasoning one. And if it's too big, then presumably it's the trophy that it is referring to. And if it's too small, then presumably it's the case that's being referred to. But if you score those independently, on average, if you always answered the case, then you'd be scoring at least 50% because you get it really right one of the two times. So you really ought to be scoring the whole thing and either giving 100% or 0% really. You may get artifacts in the data set. Here's another example from the Winograd Schema Challenge. The sports car who took the bus because it was so fast, so slow. In fact, this is not one in the Schema Challenge data set precisely because it has statistics which can help disambiguate pronoun resolution. Sports cars tend to be fast, buses tend to be slow, so that gives you a prior about which one it refers to. And then there's a paper which Ryan Burnell and many other people, including Melanie Mitchell, and I'm a co-author as well, which appeared in Science in 2023. And we talk generally about this problem of evaluating AI in general, but particularly large language models, and thinking about how to do it and making sure you don't just report average accuracy, which is what often people tend to do, because it's going to mask underperformance in particular areas. And so you really want to categorize your data set into lots of different sub areas and then make sure, and perhaps even the different difficulty levels, as we do in a paper in EMNLP with some colleagues from Oxford University. And so that you can really see where the system is doing well, or it can only do well on the large number of easy examples and fails completely on the difficult ones. As I said, static evaluation obviously makes it easy to evaluate if you have multiple choice questions, but that's not a very natural setting really for human beings. We tend to avoid that method of evaluating our students at universities, except perhaps in the earlier years, but certainly we try to avoid it in later years. And often these data sets which purport to be testing common sense reasoning aren't even really doing that. And there's also very little spatial and temporal reasoning in many of those benchmarks. So there was also another nice paper which appeared now a couple of years ago in the AIJ, which was entitled The Defeat of the Winograd Schema Challenge. And what it says, and I think completely agree with the conclusion, is just because now we do have large language models actually getting very high percentages, accuracy percentages on the Winograd Schema Challenge, it doesn't mean to say that they can now, large language models can now do common sense reasoning. The 4 lessons they they advise us to take note of. Be cautious when introducing surrogate problems. So here, these Whittaker schema challenge is a surrogate for the problem of trying to measure common sense reasoning. And it was really thought to be a really good one, but actually it turns out probably it's too big a gap between that and the general problem. And don't rely on a perceived connection between the tasks and methods, in particular, just because humans use solve a particular problem in a particular way, don't assume that machines are necessarily do the same way. They may be able to take some kind of shortcut which wouldn't be available to humans. And create tests that are really as comprehensive as possible. So many of the Whittaker schema challenge instances don't cover things like ethics or theory of mind. And there's this big tension which we have in general in AI. There's this tension between tests that are easy to evaluate and the tests that are definitive. So it's hard to, in general, you might want, for example, evaluate the explanations these systems give as well. That would give us a much stricter tension of comprehension, but it's much easier just to send a multiple choice question and just say, did it get it right or not? But that's really not testing comprehension in as thorough a way as, for example, we would do when conducting a PhD Viva with a student, and then we really probe into that student's understanding of a particular topic. So Jose Hernandez Arella and I, a couple of years ago, put a paper which is only on arXiv, but we sort of consider this alternative approach of what we call dialectical evaluation. And so you conduct an extended conversation with a system, and each question might be dependent on the previous answer. And so we're not trying to obtain the sort of average accuracy performance. We're really trying to map and find the failure modes of the system. And if there are, it might give a response, and maybe it's a little bit ambiguous. You'll see that a bit later on in one of the examples I'll give. We can really probe that. We can test what McCarthy has called elaboration tolerance. If we can solve one version of a problem, change it very slightly and see whether it can still do it. Of course, the big problem with this is it's very expensive. This requires ideally really a human spending a lot of time interacting with the LLM, which is great fun. People have suggested perhaps you could use LLM as judge, which is a sort of popular thing that people are looking into. But it's the judge is only as good as the LLM, and as we know, LLMs are flawed, so it's not a panacea. So here's another Whittaker schema challenge instance which I made up, and so it wasn't in any pre-existing data set. The book wouldn't stand upright in the bookcase because it was too small. What does it refer to? And this is GPT-4 replying. I did this sometime last year. In the sentence, it says it refers to the book. Now, I don't know about you, but certainly I think that it should be referring to the bookcase. The book is too large. The bookcase is too small. The book is large. The bookcase is too small for it to fit into. But it says it refers to the book. And then it gives some reasoning here, some justification, including this one, which is kind of very odd. That under one here, if the book is significantly shorter than the height of the shelves in the bookcase, it may not be able to stand upright without support. This is because there isn't enough shelf above the book to help it stay vertical, which doesn't seem to have any nice physical sense. And then it says, in this case, the book might topple forward or backward. Well, they're not going to typically do that. They might topple side to side, but not forward or backward. So this is really suggesting a fundamental lack of understanding about the physical world. So I then probed a little bit further. I said, could it refer to the bookcase? It says, yes, theoretically it could, but it's less likely. And it says the gender pronoun like it refers to the closest preceding noun. In this case, that would be the book. But if you look at the sentence, the book couldn't stand upright in the bookcase because it was too small. The previous preceding noun to it was the bookcase. So it can't even calculate sort of spatial distance within the sentence. And I'm not going to go into all this in every example here in a huge amount of detail, but it's clear that it hasn't really understood. There's a set of common sense problems which was originally created by Rob Miller, and is maintained by Leo Morgenstern. And it's a set of sort of challenge problems. So this has been around for many years now. But so I took one of those challenge problems from that, and this is actually set by my ex-supervisor Pat Hayes. Give a general purpose characterization of what constitutes a handle in the ordinary sense of a door handle or drawer handle, which is sufficient for one to infer a quality description of the shape of a part of the object and whether or not it can be handled for that object. And so this is now DeepSeek R1 chat mode. try to look at this when it came out, and this is actually all pretty good. This it sort of has a number of 6 different criteria here, and these are all good criteria, and all make very sense. And if you ask ChatGPT 01, I asked that, and it gave a similarly kind of pretty good, though rather lengthier answer. But then I changed the question. Again, this is in the McCarthy sense of elaboration tolerance. Suppose, can I use a blunt conical projection as a handle for a draw, such that the base of the cone is flat against the jaw? So basically the cone is pointing out, the sharp is pointing towards me. And DeepSeek says it would be likely to be impractical and uncomfortable for general use. Then there's a whole bunch of reasoning which I've cut out for sake of brevity, but it basically says, yes, that could technically do, but it'd be inefficient and uncomfortable. So this seems like a pretty good response. The only slightly odd thing here, it said flattening the tip. I already said it was blunt. Adding texture is good, but it's not clear that really flattening the tip is going to help. The problem is this thing is getting smaller towards you, and you haven't got anything to pull against when you're opening it. So I asked it, why do you suggest flattening the tip? It has one good answer there in terms of comfort, but it also says, the tip provides a clear point of contact. A flat tip provides a clear point of contact, which again, when pulling, and again, that doesn't seem to make any physical sense. If I asked ChatGPT 01, which is the latest GPT model I have API access to, or even chat access to, it says, yes, it would be fine. It can work as a handle, essentially functioning like a knob. So it's really showing much worse understanding of what it is to be a handle. And I just checked its understanding. Are you assuming the widest part of the conic section is next to the jaw or further away? And it says, yes, it is. The base is for closer to the door. So it's definitely got it wrong as not really understanding the problem here. Here's another problem. There's a set of example problems which LLMs get wrong, which is started by Ernie Davis and Gary Marcus. And this is one of these such problems. And so this is the problem of can you put 3 points in a row such that no 3 in a line. So this is ChatGPT 4's response. I'll go through some other LLM's responses in a moment, and you can see it's got it completely wrong. It's put all 9 in, and it says, and it also says you can place up to 8 points, but it's actually put 9 on here. So this has got it. It's really got it badly wrong. I said I count 9 points with 8 different lines. I apologize. These things are always apologizing. So it then says, here's a corrected one where it's better, but we've still got the 2 diagonal lines, so it's still wrong. I tell it, I still see 2 diagonal lines. Okay, now it's giving me a correct answer, but it's not the maximum. So we've got 4 points, but it claims it's the maximum, so it's still incorrect. So I now say that but it's possible to get more than 4 points. So it goes back to its previous wrong answer. Then it gives me another wrong answer, and then it goes back to the previous one. Then I give it a hint, essentially a chain of thought kind of hint. I suggest you place the points on incrementally. And now it's actually done pretty well. It's actually got 5 points. Of course, if a human being came up with that, they would instantly see that actually you could get 6, because you could have put another point on the top of that, the middle of the top line, and you'd be able to get 6 in there. But the ChatGPT 4 hasn't seen that. But at least it's now got a correct solution if it's not maximal. So I then probe it to try to push it to get more than that, and then finally it gets an answer where it does have the maximum of 6. I say, is that the only solution? Yes, you can get other ones by rotating or mirroring. Can you give me one of these alternate arrangements? No, it can't. Please go back, and then it gives me a good answer after a bit of probing. I say, is that a rotation or reflection, or both? And it says it's a rotation and a reflection, but clearly it's not. It's either a reflection or a rotation. But if you do both, you get back to where you started from. And it hasn't even got the correct set of points there. I asked ChatGPT 01. It's all about it for a minute and 20 seconds, and it instantly comes up with the correct answer. So I'm not completely convinced by this. This argument is given at the top here. A good way to see that 6 is the maximum is that you cannot take 3 points, same row or column. You can't do a diagonal, which is just what I gave you in the information. It says by simple counting, but it requires a bit more reasoning than just simple counting. What kind of counting are you really doing? But anyhow, it does at least have a good answer. Then it explains why you can't get 7, which is all good, except for this bit I put in the bit in orange. Avoiding that, you end up filling 2 per row and 2 per column, which caps the total at 6. Once you also avoid putting all 3 on a diagonal, but you don't need that. You're capped at 6 as soon as you say not putting 2 per row or 2 per column. How does DeepSeek R1 do? Not very well is the short answer. So it says I began by drawing a 3x3 grid on a piece of paper, which is kind of interesting. And so it's named the grids probably slightly less helpfully than the other ones with LLMs we saw, which used row column notation. This is clearly not as good a notation if you're trying to get a good representation. So it then starts trying to do some reasoning, and then this is all in the same response it's doing, and it realizes various things are going wrong. It tries another attempt, 4th attempt. Then it says A, F, and H. I've just put the diagram at the top right here, just so you remember how it's done, label the different positions here. It says A, F, and H are not aligned, true. F and H are in the same column, false, they're not in the same column. And then it says D, F, and H are in the second row. No, they're not. They're in the second and third rows, which forms a straight line. No, it doesn't. This configuration also fails because D, F, and H are aligned horizontally. No, they're not. So it keeps on going, selects 4 points. So it satisfies the condition, A, B, D, F. That's okay. Then it tries to, this is all in its initial response, attempting around the 5th point. And then it claims at some point lower down, B, H form a diagonal line. They form a line, but not a diagonal line. They form a vertical line. And so then it says its final conclusions are possible down the 5th point. Then it tries again with a different 4-point configuration. Actually, just go back here. Actually, you could see it wouldn't be impossible because you could add H and I to this. So it's clearly not impossible. So yeah, ultimately it goes on, and eventually it comes up with a solution, which of course isn't a solution. And it says no 3 x's are aligned horizontally or vertically or diagonally, which is wrong. Okay, that's all I want to say about that. But that was kind of an example of this kind of dialectical style of evaluation and just showing you the difficulty of LLMs have with this kind of problem. I mean, it is the kind of thing that if you and I as humans were doing this, we would get out a paper, we get a paper and a pencil, and we'd start just drawing things. And so doing this purely linguistically is likely to be more challenging. So this is a paper which appeared in COSIT 24, jointly with my research fellow, the Turing Institute, Rob Blackwell. So we were trying to test to see how well these things could do about reasoning about cardinal directions. So we created 2 data sets, a small, simple one, but 100 simple questions where the answer was either north, south, east, or west. And here are a couple of examples, or a large one, which was template-based. And so we had these 6 different templates. So we had, you are walking south along the east shore of a lake. In which direction is the lake? And so I've highlighted these different bits because those are the bits in the template you can change. So we allow, instead of having saying you are, we can say we are, he is, she is, they are, and so forth. Instead of walking, we can say hiking, pogo sticking, perambulating. For the yellow ones here, we can substitute the different cardinal directions, also including the intercardinal directions such as southeast, northwest. So some of these are very straightforward. The template 2 is interesting because you set up initial scenario, then head back in the other direction. Of course, actually, since we're not in this data set asking about left or right, actually the direction you're facing is irrelevant. The only thing that's relevant is which shore of the lake you're on. The difference between 1 and 5 is interesting because if you're on the east shore of a lake, the lake is to your west. But if you're on the east shore of an island, then the sea is to the east. And then there's this one here, and the template 4, which as we'll see, causes them a lot of problems. Almost all of the language models have problems. You're walking east along the south side of a road, which runs east to west is the direction, which direction is the road. The other templates all have a sort of aerial object, a lake, a park, an island, the sea, but this one has this linear object, and that seems to cause rather a lot of problems, as we'll see. So we tested a whole bunch of large language models. The one in blue are the ones which we were around at the time that we went to press with the COSIC paper. And then as new large language models have been coming out, since then we've been testing them. In the original paper, we only ran each experiment once. Since then, we've done it more times for as much as we could afford. Generally, it's 3 or 5 times. You can see that this is for the small data set. So we've got the results here, both at 01, which is now getting very good at 0.98, and DeepSeek, the reason at R1 with the API interface, which is pretty good at 0.96. In all these cases, we were using a fixed seed where available, and also setting the temperature to 0 where available. And where we've got a repeats, then we also give the confidence interval. For the larger data set with those 6 templates, you can see this was much more challenging. Things like OLAM are doing really very bad at 0.2, still better than chance, but remember we've got 8 possible answers here, so it's I guess 0.12, 12.5% would be chance, but it's still not great. For the 0.01, we only ran this very recently because we only got access recently, so that was only ran once. But we're getting, not 100% yet, but pretty good at 0.92. We've tried very hard to get the DeepSeek R1 results out of this, but we've had all kinds of problems. They've had denial of service attacks, and our jobs kept on falling over. So we still don't have the results for that, unfortunately. But they'll be out soon, no doubt. So I don't know how well that's going to perform compared to 01. Previous to that, a Claude 3.5 Sonnet was the best. At the time of when we put the paper in, the way to camera-ready copy for the paper, interesting, 3.5 Turbo was actually the best one, beating, for example, GPT-4 Turbo. So if we look at the confusion tables for this, so this is the 2 top performing models. And what you can see is that for the cardinal directions, northeast, southwest, we've got pretty good. Things are less good for the intercardinals, though if 01 is getting better on, it's better, but we're still getting some confusions. What's interesting is that you get this asymmetry of confusions here. So north gets confused. If it's thinking it should be south, it's likely to predict north, but if it's thinking it should be the south, is much less likely to predict north, but in fact it predicts more likely to predict east. So these confusions are not always symmetric, and you see that happening again here, where northeast and northwest get confused with each other, but southeast gets confused with north. Southeast gets confused with northeast, and southwest gets confused with northwest. And these are some of the. This is now looking at the results per direction. So we've got 01 is here. So yes, this is just some of the other models, and you can see in particular some of these less performant models. Although we're pretty good at the cardinal directions, we definitely have this sort of asymmetries here, or this symmetric. Confusions down here at the bottom part of the intercardinals. And so in these sort of squares here, basically what's happening in that case is northwest is getting confused with southeast, and northeast is getting confused with southwest. So we can actually look at the different subcases, the different kinds of values for the templates individually. So we look at how some of these different models do on directions. So this is a Claude 3.5 Sonnet, and you can see that interestingly it does rather bad on north, but it does reasonably well on south and east. Southeast is somehow much better than the other intercardinals, and west comes in the middle here. So why are those outliers? It's not clear. This is for a mean score for answer direction. For other ones, here's 01. where at least we expect the cardinals to be the easiest, and indeed that's the correct. That's also the case for GPT-4o and for Llama 3.7b. So east is always in the top two, except for Llama 3.7b. If we look at locomotion analysis, this is kind of interesting. So this is for Claude 3.5 Sonnet. We've got here hiking comes up top. Unicycling, perhaps not, and perambulating, not perhaps surprisingly, come out bottom there, much less likely to appear in training data in terms of words. You might have thought the walking would beat hiking. We wondered whether that was because in American English you tend to say hiking more than walking, but if you look at the stats of some of the possible training data sets, that's not true. Walking is much more common. So it's not at all clear why walking is much worse than hiking. But of course, a human, this wouldn't make any difference. I mean, we can abstract away from the method of transport, and we're just going to focus on the fact we're moving in a particular direction and we're in a particular place. So this is 01 for the transport modes. And here hiking again is best, but sometimes for GPT-4o driving is best, and it's also best for GPT-4o mini. And yeah, so here, whilst here driving is pretty well down, whilst driving is top here for this. So these different LLMs really perform quite differently. The person form analysis is rather interesting, and we see this particular happening across quite a few of the LLMs. Note this x-axis doesn't start at 0. This is a particular one that's starting at about 0.65. So you can see there looks like there might be some gender bias here, even taking account of the confidence interval. So she is worse than he is. The first person forms, I am, we are, seem to be doing better than the third person, the second and third person forms. Not all models seem to show gender bias. So for example, so this one here, GPT-4 Turbo is slightly better for she is than he is. Also, I thought there's another one which I don't have up here, but in general, yes, here's another one, Llama 3.7b Instruct. So if we look at mean score by template, and this is what I said earlier about template 4, you can see that template 4 is the red one here, and you can see in all cases template 4 is the one which is creating problems. It's always much lower, even for GPT-01, which is this one here, where we're getting pretty good scores on the other templates. It's the template 4 which is bringing its score down. So we need to investigate these kind of linear objects much more. We looked a bit how does accuracy vary in temperature. So this is just done with GPT-5 Turbo, and you can see that as you increase the temperature, which is kind of what other people have observed as well, for reasoning you really want to have temperature 0. For creativity you want to have higher temperatures, but for reasoning you like to get better results with lower temperatures. Just a couple of amusing quirks. In GPT-5 Turbo, we had one answer which include both Latin and Chinese characters. South something or other, east, which apparently means south, S French German, H east, and also it invented this new cardinal direction Kest instead of west, as I north Kest. We started thinking, well, how many times do we need to actually run each of these tests in order to get good confidence intervals out, but without spending huge amounts of money in actually repeating the experiments multiple times. So we did an experiment involving the COSA data set, and we tried it on these 6 different LLMs. We had the 2 different cardinal direction data sets I've just talked about, and we compute the prediction interval, which is the estimates, the range where future observations or means of observations will likely fall. And this is what we see. So we've got the red dashed line is the point where the prediction interval falls below 0.01. The odd columns here, so this one and this one, are where we have the default parameter settings, and the even columns, so this one and this one, and where we set temperature to 0 and a fixed seed. And you can see if you do that, then you either immediately or very quickly get to very small variation in possible responses. The only one where we get completely deterministic answers is Llama 37B. That's the only one model which is small enough to be able to run on our own laptop, our own machine. And so in that case, where there's no non-determinacy arising from running these things in the cloud. And this is, again, something that's been remarked on elsewhere. You get this non-determinacy. And well, as soon as you go into the cloud running across multiple machines, which seems to give you some basic variations in the answers. This is a few more LLMs, and you see the same thing with the as soon as you set the temperature 0 and seed to fixed, you get predetermined deterministic responses. So basically, our moral from this was that 3 seems to be a good number, and obviously we need to do more testing across multiple data sets, but certainly based on this, if you want to, 1 is clearly too few, but if you do it, repeat the experiments 3 times, that gives you a reasonable idea that you might be getting a small prediction interval. As I've said on this slide here, yes, I already talked about deterministic results, and obviously we need to do this on further data sets. So let me move on to the next set of experiments we did, which was looking at the qualitative spatial calculus, region connection calculus, which for anybody who doesn't know it, you see it illustrated here. So we've got these 8 pairwise disjoint and jointly exhaustive relationships, disconnected, externally connected, partially overlapping, tangential proper part, non-tangential proper part equals, and these 2 being asymmetric relationships and inverses here. And we're going to, and let me just explain the arrows, but we're going to come to that in a moment. These indicate the so-called conceptual neighborhood diagram, which tells you if you've got, assuming the regions are moving or translating or deforming continuously, then you can't get from disconnected to partially overlapping without at least instantaneously going through external connection. And you can't get from external connection to, say, EQ without going through partial overlapping. And so we're going to see whether large language models can actually figure these arrows out in a few slides' time. So the most common form of reasoning with qualitative spatial reasoning is the so-called compositional reasoning. So given R1xy and R2yz, then what are the possible relationships between x and z? So here's a pre-computed composition table for RCC8. And if you, for example, know that x is a non-tangential proper part of y, and y is a non-tangential part of z, then this tells you that that x is a non-tangential part of z. You see, in some cases, the answer is not unique, as it isn't here. In some cases, like DC, actually all 8 relations are possible. So the question is, could an LLM actually compute this composition table for us? Typically, these things are often built by hand. Sometimes they had some automated reasoners or models used to try to do this. And so we had the initial prompt I'll show you at the moment, which describes the relations. It mentioned RCC8 by name, so it could bring any external knowledge it had from training. And then we then prompted the LLM, in each case in a separate conversation for each of these values here. So we tested on 6 LLMs of different sizes. And here's the prompt. So the colored here as the bit that's explaining what the different relationships mean. We allowed it to quote, to think, reduce some chain of thought reasoning if it wanted to, whilst it did it, but we asked that it always did the answer in the form # answer : so we could easily and automatically extract the answer, which was almost always the case, but not quite always. So, for example, if DCXY and DCYZ, what's the relationship between X and Z? And so we haven't tried O1 or DeepSeek on this yet. There's a paper on Archive which presents these results. The best to worst model, 3.5 Turbo is right at the bottom, 3.5 Sonnet, 3.5 Turbo was the worst model, which is at the bottom part of this slide. 3.5 Sonnet is at the top of the slide. On the left, we've got the absolute values for the different relationships. And at the top is we've got the relative values. So the dark greens means it predicted a relation for that particular cell table entry, and it was correctly present. If it didn't correct it, if it didn't predict it for that thing, then it's colored light green, it was correctly missing. If it predicted it, so it said it should be present, but actually it shouldn't be, we've colored it dark blue. And if it should have put it in there, but didn't, then it's light blue. So you can see that, you know, it gets DC is one of the easy ones to look at, but EQ is one of the harder ones. So if you then look at the sort of something like a confusion table for, again, the same two models, this is GPT-3.5 Turbo at the bottom and 3.5 Sonnet at the top. And so the greener the yellow, the better. And you can see, yeah, 3.5 Turbo is in general much worse. It's much bluer and purpler. The ones which are better, the ones which are harder are these things involving non-tangential part and non-tangential part and inverse. There's another experiment in literature by Ranier et al., where because you have these multiple possible relationships, there previously been also some other work with the L interval calculus, where people tend to have a preferred relationship. So in this paper by Ranier et al., they asked into groups of German Mongolian speakers whether which is their preferred relationships, and this is this is the overall across all LLMs, I think. And you can see it's doing fairly well in some cases, but do LLMs agree? Better than chance, but no, not really. Finally, just quickly mention this. We tried to see whether they could recompute the composition table, and that's on the continuity network. And so again, green means it got it correct, and red means it got it wrong. And so again, but even the best model here, which at the time of doing this paper was 4 Turbo, it was still got quite a few wrong. So summary statistics across all 3 experiments, you can see that 3.5 Sonnet was generally the best, except for in this case here. These even numbered columns here just refer to the fact we ran the experiments twice, once where we used the RCC8 relation names, and we said in the prompt that it was about RCC8, and another one where we anonymized all the relation names, we just used random made up relation names. And you can see in general, when we anonymized relations, it did worse. And GPT-4o was newer than the GPT-4 was worse, which is kind of interesting. So anonymous, as you can see here, is much worse than the eponymous. So that you do wonder whether the thing's really just statistical powers and somehow have learned some information from its training data. Although all the composition tables in general are presented in the form of actual tables in the literature. Let me skip that. I'll just briefly mention there's just some work we've also done, which is reported in AAAI last year, where we looked at combining natural language models within symbolic reasoners, in this case, an answer set programming. So this is a data set where you have a set of statements like this, and this diagram on the right shows you what these things are doing, but is not available to the large language model. And then there are various results here. This ones colored in blue are the one I want you to look at, which is when we used a large language model, 3 different ones, to translate it into a symbolic notation, which was then given to our answer set programming system, which then was able to get 99 or 100% for each of the different numbers of steps. At the bottom here, you see when it doesn't have resort to that AISB reasoning, just does it just using large language models, perhaps with chain of thought or tree of thought. And occasionally you can get 100, but in general, it's rather worse. And I did have some stuff on multimodal stuff, but I'm just about out of time. So let me just point out that these things are terrible at generating maps. This is supposed to be plotting a sea route from Southampton, which is not here, Southampton down here, down to Barcelona, which is way down here. Even when I say try to use modern maps, it doesn't do it. It can't swap blocks accurately. If I would give it an image of a room and ask it to describe it, and analyze it. It's not terrible, but again, it gets things wrong. If I give it a simple sketch map, again, it's not terrible, but it gets quite a lot of things wrong. And if I ask it to plot a route, say from the fishmonger to the school, it says, well, head right, but it's not, it should be heading left, east. Well, actually, it's west, until you reach the intersection with the green road, and then it says turn left. Well, you don't want to be doing that. And then it says intersection of the red road, turn right, northeast, was actually northwest. So yeah, not great. This is just, I couldn't resist showing you this. Again, just showing you how bad these things like DALL-E really are in terms of understanding the physics of the world. So draw me a picture of a cat sitting on the table with a spilled bottle of milk. And superficially at first sight, this looks great, doesn't it? There's a nice picture of a cat, very cute. There's some milk there, there's a bottle. But what is this milk coming out of the bottle here when it's not broken? It's just somehow seems to be leaking through the side of the bottle. Okay, summary, quick tour of the spatial capabilities of LLMs. A diagram interpretation poor, better than chance, but you know the more modern language models clearly are doing better. But spatial reasoning is clearly core to common sense understanding of the world. There's a question about whether it can really be acquired without embodiment. And perhaps you do have to do symbolic reasoning, as I showed you briefly with that experiment with AltaSet programming as well. Dialectical and evaluation is really good, but it's expensive. Comparison with self-driving cars, I'm almost finished. If you look at the Tesla website, it says autopilot enables your car to steer, accelerate, and brake automatically within its lane under your active supervision. And so arguably there should be a similar statement for large language models, and then should always be used under your active supervision. Yes, you might be amused if you haven't seen this. This is the effect of how we all seem to be using, or at least some people seem to be using LLMs in writing their papers. And these are just for 4 different words and showing you greatly increased frequency for those words post the launch of ChatGPT. And there's a bunch of other papers since when this one paper came out, which try to analyze that. So this is my very last slide. Many thanks to my co-workers, particularly Rob Blackmore, my current research fellow. There's some future work, which I won't talk about now there, but perhaps we can come to in some of the questions.
Okay, so thank you, Tony, for your great talk. I don't know if Bertie have some questions, or I can probably start. I mean, a very preliminary question is the following one. So, did you use different prompting techniques? For example, did you use or different setting, like, I don't know, few shot learning, or did you just use the one shot learning, let's say, classification task, or do you use, for example, I don't know, the chain of thought? Did you use, I mean,
the answer is basically no, except in the case of that work with the step game, where we did explore some of those, and we did use chain of thought and so forth, and tree of thought. One reason for not doing that is, we wanted to see what the out-of-the-box performance was. But the other thing, if this is supposed to be common sense, you know, if I'm asking my 8-year-old child a question, I don't want to have to think about how to phrase that question to that child. If I'm asking him a simple question about the spatial world, you know, I should just tell, providing it's not expressed in a really convoluted way, but if the question is expressed simply, then, you know, you'd hope that the system could understand. Yes, of course, we could try to elicit better behavior, better results by having prompting strategies. The problem always is, you know, you need different prompting strategies to work better for different tasks and different domains. So it's, you know, it's a bit of a slippery slope. But the basic answer is no.
Okay. I don't know if Bertie was to jump in.
Yeah, just a quick question from my side. You've very impressively shown that some of the shortcomings in terms of spatial reasoning, common sense reasoning of LLMs, and others have indeed shown that similar results will be obtained if you use mental imaging with LLMs. My question is, do you think this is something that's inherent in LLMs, or is there a way that their models can be improved by modifying the training data, etc., to overcome these shortcomings and make them better in the future?
So, I mean, I've been looking at this since October 22, and I've been tracking the different large language models that they've been coming out, not all of them, but a good percentage of them. And yeah, the performance has generally been getting better. If you look at those charts I was showing earlier, generally the newer, the larger models tend to do better. There was another nice paper from Kevin Leighton Brown at UBC, where he was looking at rational decision making, and again, the larger the model, the better decision making he was able to note. But even in the best models at the moment, we're still seeing some odd results, and they're not, they're showing a fundamental. They might do very well a lot of the times, but then they show fundamental misunderstandings, which you wouldn't think they would do if they were really understanding the spatial world properly. So, I mean, I did say a few slides back, can you, the way we humans acquire knowledge of spatial reasoning is by being humans, and we live in the world. As babies, we play with toys and we drop things, and we spill bottles of milk and all the rest of it. And that's how we gain our knowledge. So, can any kind of computer system gain that kind of knowledge without actually being embodied? Maybe it can gain a lot of that by learning in a virtual world, and people are looking at that, and it said that we have plans to look at that more, and that would help. Of course, that's still not completely as rich as the real world. I mean, a lot of these automated driving cars, they trained a lot in virtual worlds as well, and that clearly does seem to improve performance. But whether you can really get human level performance without being embodied, I would like to say no. It would be in a way surprising if they could get it purely from textual training data. It would seem, I would be really surprised. So in many ways, I'm not at all surprised by the fact that the models here, which are only trained basically on linguistic training data, symbolic training data, that they do fall. And in many ways, I'm surprised how well they can do just learning from that. It is a surprise to me. And I mean, now we are getting, say, up to 92% on that cardinal direction one. Though I've also done some experiments which are not reported, where I ask it about left and right, and the performance drops there. I mean, it's reasoning about cardinal directions is easier because it's not dependent on your orientation. But once you have to think about which way you're facing and worrying about, allocentric and egocentric frames of references, then that becomes definitely trickier.
Okay, so if I can jump in, if I understood correctly, for your hypothesis, at least, is that with visual language models, okay, so this kind of multimodal type of language models, still, I mean, you could do eventually better than language model, let's say, alone, even if also in this case we don't have, let's say, this embodiment, so this part. So did I understand correctly, or? So
what was the question? Is multimodal going to do better?
Yeah, if you have this kind of visual language model, so this kind of multimodal, this could be.
And I think something that I've been particularly interested in looking at, I'm planning to look at, but partly I'm hamstrung by the fact that, as I showed you, their ability of these systems to actually to be able to interpret diagrams reliably is rather limited. But maybe we need a secondary system which does the parsing of the diagrams. But it would be interesting to have a system which actually tried to sketch a diagram first of all, and then started postulating possible diagrams, analyzing it, and then coming back. So think of that 3 in a row problem. the way you and I would do that, if we're not good enough to do it in our head, is actually start plotting, drawing different possible configurations, and then playing around. And if you could do that, the two things combined together, you've got the language model understanding the original question, and then maybe doing some of the inference once it's got the analysis from the diagram interpretation, and then potentially suggesting what a new configuration, if the previous one failed, might be good to look at next. So that that the interactive multimodal thing is kind of interesting, and also with the at the moment with the use of the ASP, I just showed you that in the AAI paper as just being one way. The LLM analyzes the problem, generates the symbolic representation, the logical representation, and gives it to the ASP. But it might be that there's some other background knowledge which is required to answer the question. We actually preloaded the ASP with all the sort of background and spatial knowledge. But supposing you started off with empty ASP, now you want to get not only translate the question of which has been posed, but also the background knowledge of what north and east and south, west meaning, the fact that west is the opposite of an east and so forth. So you might put it into the ASP and it says, I don't have enough information. So you might go back then to the LLM and it tries harder to try to extract some more domain knowledge. And again, I've got a student looking at that. It's just starting now, I hope.
Okay, that's good. I don't know if there are other questions or, let's say, comments, curiosity. I don't see any additional question from the chat. So if not, I would like to say thank you again to Tony Cohn for this great seminar, and thank you also to Bertie Müller. And see you for the next talk that will be provided by Bernardo Magnini on February 27. So, bye. Thank you, Tony.
Thanks so much indeed for your time. Thank you.